What's up, AP Calculus students? Mr. Ford here with another homework tutorial. This is 4.2.3. We're going to do all the problems here. There's a lot of easy ones. There's some a big one near the end, but I think we're going to be okay. This should be one of a shorter video. So here we go. First thing we got to do in these first questions in 470 is to rewrite the integral expressions as a single integral. So we're combining ideas together here. On question A, I noticed that the bounds are exactly the same on both integrals, so that means we can just subtract the two integrand parts of this. So this would be the integral from -5 to 2 of 6x to the third minus 9x, all in parentheses, times dx. Just combining the two green parts together. Pretty simple. Question B. This time I noticed that we do not have the same bounds. We have the integral from 5 to 9 and the integral from 9 to 3. So the first thing that I want to do before we do anything else is rewrite this as the integral from 5 to 9 of some function h of x dx plus the negative integral from 3 to 9 of some function h of x dx. So what this will do, let me move that down a little bit. So what this will do is it's actually going to take, well, if you think about this for a minute, it's going to take the area from 5 to 9 of some function and subtract the area from 3 to 9. Now, the area from 3 to 9 presumably is going to be bigger than the area from 5 to 9. So what's going to be left with, there's a couple different ways we could think about it. You could think about this as the negative integral from 3 to 5 of h of x dx, because that's what will be left over. It's the integral from 3 to 5, but the opposite of it. You could also apply the same kind of thinking we did for the first step and write this as the integral from 5 to 3 of h of x dx. Those are the same idea. That would work. Okay, next question. Question C. Again, I think C is very similar to A. I noticed that the bounds are exactly the same, 2 to 7 and 2 to 7. So all we're going to do here is we're going to combine together these ideas into one integral. We're going to do the integral from 2 to 7. We're just going to add together the two integrand parts. It'll be pi times 2x squared plus pi times the square root of x squared dx. One note about this, you could factor a pi out of this problem, since pi is just a constant. So you could rewrite this as pi times the integral from 2 to 7 of just 2x squared plus the square root of x squared. In fact, you could do square root of x squared is just x, but that's unnecessary. And this would all be times dx, like this. This is setting up for a concept we'll deal with later, but it's a preview question, so keep that in mind. And here we've got the integral from 1 to 4 of x plus 5 squared dx and the integral from 6 to 9 of the square root of x dx. And I don't think there's anything we can do with this. I don't think there's anything that I can do to make this happen. I suppose if I wanted to translate this, I do notice that here's one thing we could do. I do notice that 1 and 4 have a difference of 3, and so do 6 and 9. So what you could do, you could translate either one of these integrals to match onto the other one. So that's not difficult to do, really. We did it way back in 4.1.3. Not that I expect you to remember all that, but what you could do, you could add 3 to both these integrals. Would that do the trick? No, you need to go to get to 6 and 9, you got to add 5. 1 plus 5 and 4 plus 5. If you do that, you have to subtract 5 from x inside of the parentheses. So I'm going to rewrite the first integral as the integral from 6 to 9 of, in parentheses, x minus 5, close parentheses, plus 5 squared dx, plus the integral from 6 to 9 of the square root of x dx, like that. So what's going on there is I added 5 to both of the bounds, and I also subtracted 5 from x because that's how you translate it to the right. You can translate the boundaries by adding, and then you translate the function by subtracting, but those both move the whole function off to the right. And now the boundaries match up, so we can combine them together. Not only that, but we have some simplification that will happen inside of this right there. -5 plus 5 will cancel out, and you'll have x squared. So one integral would look something like this. You would have one integral from 6 to 9 of just x squared plus the square root of x times dx, like that. That's kind of advanced for this, but that will do the trick. It's a pretty cool problem. Okay, 471. Kylie put his dog on a diet. If f of t represents pounds lost per day and t measures in days, what does the integral from a to b of f of t mean? This is a great problem because it really gets away from the area model for integrals and really starts talking about how we're going to use them in many different story problems, and that is to think about accumulation. F of t, I want to point out, is a rate. It's pounds lost per day, and the key is per day. So when you do the integral, what you're going to do is you're going to accumulate all of those rates and actually find out how much weight was lost, and that's exactly what it is. So the integral from a to b of f of t dt is going to tell you how many pounds the dog has lost. The same way that when we integrate velocity, we end up getting distance. If you integrate the rate you're traveling at for many small times, you end up getting the actual distance traveled. This is the exact same concept, except for instead of like miles per hour, it's pounds per day or something. But when you integrate, the per day drops off and you just get the pounds. It's exactly the same concept, just applied to a more general idea. Let's take a look at 472. We're going to review some limit questions really quick. This will not take us a super amount of time. The limit as x approaches -1 of f of x does not exist because of the vertical asymptote going on in that problem. So there is not a limit there. The limit as x approaches 2 of f of x also does not exist since it is approaching a different idea on the left as it is from on the right. So that's another DNE. The limit as x approaches 2 from the left, though, does totally exist. If you look at just the left side right here, you're approaching a y value of, I believe, 2 right there. So that is equal to positive 2. The limit as x approaches 2 from the right is the same concept, only you're approaching from the right this time. Looks like we're approaching -2 if I have to eyeball that really quick. By the way, it's because those two answers are different that the answer B does not exist. Question 5, the limit as x approaches 5 totally exists because it's just approaching the same thing on both sides. Very boring there. I'm going to eyeball that as a 2.5. Right there. And the limit as x approaches infinity of f of x, that would be kind of the horizontal asymptote going on over here, looks like a pretty solid 0. Looks like it's going towards 0 and never actually touching it. G asks, where, if anywhere, does the derivative not exist? So I see a bunch of different places. X equals -1 is a continuity problem, and x equals 2. There, the graph is not continuous. And so, therefore, it is not differentiable there. I don't see any sharp corners on this graph. I don't see any cusps, so those are other places where it would not be differentiable. 473, the graph right shows the velocity of an object over time defined by the function, this function. We're going to use our graphing calculator to evaluate the integral. Let's go for it right now. Calculator cam, summoned to the job. Here we go. All right, turn that puppy on, clear out whatever's there. Alpha F2 is going to bring up this menu. You want to select Fn int, and you can go ahead and fill in all the spaces. 0 to 4 of -0.5x squared plus 3x plus 1 with respect to x. I'm actually not sure if you could use t there if you wanted to and then put dt in there. It would probably still work, but 17.3 repeating. Or 17 1/3 if you want to be so particular, which is cool. Bye-bye, calculator cam. What does the result in part A calculate? Well, just like that dog losing weight question, this is the velocity graph. If we integrate it, it will the feet per second of this will drop off, and we will just have the feet. So this is going to calculate the distance traveled. Distance traveled in feet, specifically from t equals 0 to t equals 4. That's important because that's the bounds of the integral. 0 to 4, 0 to 4. The more you play around with integral notation, I hope you're seeing how useful and powerful it is. What does the derivative of the velocity mean? That means the acceleration of t. And the units of the acceleration would be feet per second squared. Feet per second per second. I'm going to put 2 e's in the word feet because that's how it's written. Feet per second is what's going on there, the acceleration. Okay, 474, we're going to evaluate some integrals based on a given integral. So we don't know what the function is, but we do know that the integral from 2 to 4 is equal to 10. So here's an interesting one. The integral from 4 to 2 of, let's see here, the integral from 4 to 2 of negative f of x. Well, here's the thing. This is equal to the negative integral of negative integral of 2 to 4 when you flip the bounds around. As far as that negative sign right there in front of f of x, you could think about that as a negative 1 that can then factor out and cancel out the negative in front. So this is just equal to the same integral, which is equal to 10. And that's that. For B, I noticed B and C are both going to be one of those horizontal translation problems that we've dealt with here. So what I noticed what's going on here is that it looks like 2, they added 10 to 2 to get, or maybe 8. They added 8 to 2 to get 10. And they added 8 to 4 to get 12. And they subtracted 8 from x to slide it to the right 8 spaces. So this is going to be the same value. Then there's that plus 4, though. This has got a vertical translation of 4 on it also. So what we've got here is we've taken the original graph. You want to think about this. Here's 2, here's 4. We have some function, doesn't matter what it is, but the area under that curve is 10. That's kind of what the original integral says. We've taken that integral, shifted it some 8 steps to the right where it does not change, but then we've also shifted it up 4 spaces. So we've got the same basic shape, which has got 10. We've also got a little chunk under it, which has been shifted up 4 spaces. And that little chunk still has a width of 2 because the bounds are still 2 apart from each other. So what we're going to do, we're going to take that original 10 and we're going to add 4 times 2 to it because that would be the area of this rectangle here. And that will be 18 for the final answer there. I don't think we can calculate C. I think C is meant to be kind of a trick problem for us, and I'm going to go ahead and submit that I don't have any idea what that is, and here's why. Because we have translated the bounds of 10 and 12 have still been translated by adding 8 to the original bounds. But now we're adding 8, which is going to move the thing to the left instead of moving it to the right. And so I'm going to say that since the boundaries translated to the right and the function translated to the left, there is not enough information. This is one of those ones that when I'm done with this video, I'm going to go look up the answer to the book published and see if I'm correct. We'll see. I think I'm right, but we'll find out. Next question, 475. We're going to, given this function of f of x equals 2x, we're going to write the equation of a vertical line that will divide the integral from 0 to 10 in half. This question might get a little hairy really quick. I'm kind of nervous about how this is going to go, but I think I know what to do, so we'll find out. First thing we got to do is think about what this would look like. We have the function 2x, which has a point at 0, 0, and a point at 10, 20. So I'm just going to kind of sketch a triangle for this. This is what our integral from 0 to 10 would look like. It would just be the area of this triangle. This triangle is 10 wide and 20 tall, so its area is equal to 1/2 times 10 times 20, which is half of 200, which is equal to 100. And that's all well and good. What we're looking for, though, is the line, some vertical line x, which is going to cut this into two equal sections. And that is not going to be an easy thing to calculate because the two sections are going to be two entirely different shapes. So the first side is going to be this triangle here, and the right side is going to be this trapezoid. It's actually not going to be too tough, but we have to think really carefully algebraically about how we can express all of the parts in this problem. Let's start with a triangle. The triangle is going to have one side that is just going to be x, because we don't know where that x is going to be. And we do know that the height of that triangle is going to be 2x, right there. So that's the first step. The triangle has the area 1/2 times x times 2x, like that. We could simplify this to be the 1/2 and the 2 will cancel out. It's just going to be x squared, which is actually kind of an interesting idea if you think about it. But that will work. The trapezoid, the green part of this problem, is going to be, well, let's just break it down a little bit. We got to think about, again, how we can express the different parts. This side here is going to be the same 2x as it was before. This side is still going to be 20. And this distance, the height of the trapezoid, is going to be 10 minus x. So if we put this all together into the trapezoid formula, it would be 1/2 times the sum of the bases, 2x plus 20, times, in parentheses, 10 minus x, which is the height of that trapezoid. Our objective here now is going to be to write an equation that is true about these two things. I mean, they need to be equal to each other, I guess is a good way to think about that. So best way to do this might be to apply this 1/2 first and have x plus 10 times 10 minus x. Oh, that's going to be nice. Let's see. We'll have a negative x squared. We'll have a positive and negative 10x, so those will cancel out, and we'll have a plus 100. Cool. It's actually not too terrible. So really, we just need these things to equal each other. We need x squared to equal negative x squared plus 100. So to do this, we'll just add the x squared to both sides, and we will solve it as we would normally. We'll get 2x squared equals 100. We'll get x squared equals 50, and so x is going to be the square root of 50. I am aware that the square root of 50 has two answers, but we don't need the negative one in this problem, since everything in this problem is in the positive zone. Square root of 50 is 7.071, and that would be, I believe, the correct answer to this question. Oh, calculator Cam, come on, focus. The people need your answer. There you go. Not too bad. That problem's actually pretty cool. That's a good example of an old school calculus problem that doesn't really have anything to do with calculus, but is really heavy on the algebra. You don't see these on the AP test very much anymore, but they used to be all over it. 476, we're about to approach the 20-minute mark, so I guess I was wrong about this one being a short one, but these last two problems are going to be pretty quick. 476 looks big, but it's actually going to be pretty simple. We are not allowed to use a calculator on it, though, which is good practice. However, we got, very similar to yesterday's homework, we got two problems involving distance and velocity, so let's compare. Question A says that as an arrow flies through the air, if the distance has traveled in feet is given by this function, s of t. Without our calculator, we're supposed to determine s prime of t at 1, 4, and 16 seconds. So just like yesterday's problem, we're going to take the derivative and plug a bunch of stuff into it. Our original problem, s of t, is 4 square roots of t. I think it's better to think about this as 4 times t to the 1/2 power. Because then the derivative, s prime of t, which is the velocity, is going to be 2 times t to the negative 1/2 power, because the 1/2 times 4 will make it 2, and the 1/2 will drop down by 1. This might be better expressed as 2 over the square root of t, like that. Now we require the answers to some problems here, s of 1, 4, and 16. Or sorry, s prime of 1, s prime of 4, and s prime of 16. So we're just going to plug that in. 2 over the square root of 1, 2 over the square root of 4, and 2 over the square root of 16. In general, you'll find that if a question on the AP test does not require a calculator, then it's usually pretty easy to evaluate in the old noggin. This is going to be 2. This is 2 over 2, which is 1. And this is 2 over 4, which would equal 1/2. So there are the 3 answers for part A. As far as the big concept that we used in this problem, we used the derivative of distance to find velocity. We'll rehash that in a minute here, but that's the case. Question B is going to go the opposite way, just kind of like yesterday's problem. Oh shoot, I hate when this happens. Buddy, I'm trying to do like a thing right now where I make videos for my students. I don't want to scroll through this entire document over and over and over and over again. Man, it took me all the way back to like 4:14. I apologize for this, anybody who's watching this video. This is bad production quality. And if I had more time, I'd go back and edit these and get rid of these sections. But you know what? Who's got that kind of money? Question B. As a train travels past the station, its velocity is measured in miles per hour, is given by v of t equals 9t plus 32. The train is directly across from the station when t equals 0. Determine the position of the train at t equals 1. So, we're going to use the area under the curve to figure out what's going on. Basically, what we're going to do is we're going to take the integral from 0 to 1, since it's 1 hour, and everything's a mile per hour, of v of t dt. So to do that, the only powerful tool we really have right now is to find the area under the curve, and this is just going to be a straight line. So it's actually going to produce a trapezoid. Here, I'll show you. So our function v of t is equal to 9t plus 32. And we want to evaluate this function from 0 to 1 of v of t dt. It's not super necessary for us to draw this drawing exactly to scale, so we'll make it as easy as possible. I know that at 0, it's at 32 because of the y-intercept of 32 on this thing. And I'm just doing some quick little head math. After 1 hour, 9 plus 32 would give me 41. So I know the point here is the point 141. And that's going to be the other point of this. So evaluating this integral is going to be as easy as finding the area of this trapezoid. We know this side is 32, we know this side is 41, and that side is 1. So this will actually be pretty simple to do. This is going to equal 1/2 times the sum of the bases, 32 plus 41, times our height of 1. 32 plus 41 is going to be 73. 73 divided by 2 is going to be some number, it's 36.5. And since we went from velocity in miles per hour, this is now in miles. I guess I missed that in the last problem. These should all be in feet per second, I think. So one more time, revisiting this question C, which is the same question as it was yesterday's assignment. Both these problems involve distance and velocity. However, the relationship between distance and velocity is basically this. You have distance, usually written as s of t or x of t or something like that. If you take the derivative, you're going to get the velocity function. If you take the integral, or the area under the curve, you'll get back to the position function, like that. Great. One more quick thing we got to do is 477, a very visual problem here. This is going to give us this. All we know is that f of t is either even or odd, and we're going to be given some integrals to evaluate. So let's start with the odd ones. If it's an odd function, then it would reflect around the origin. It would look something like this. It would come down here and then go back that way. This appears to be the point. I'm going to call that point 4, 4. I think that's what I see. So this point right there would be negative 4, 4. That will help us with some calculations. Negative 4, rather. So if it were an odd function, it would look something like that. As far as g of negative 3, this would be the integral from 0 to negative 3 of f of t dt, which, based on our integral rules, would be the opposite of the integral from 0 to positive, the integral from negative 3 to 0 of f of t dt. So really, we're just going to find the area of the curve between negative 3 and 0 right here. And we're going to make it negative when we're all done. That is just going to be the area of a triangle. It's going to be 1/2 times 3 times 3. It appears to be the case. 1/2 times 3 times 3, which is going to be 9 over 2, negative 9 over 2, which is why the answer to our problem is actually going to be positive 9 over 2. like that. As far as 2 times g of negative 7, well, let's just apply a little bit of the thinking from that same problem here. Negative 7 is going to take us all the way back here, I think. To perform this operation, it's probably a good idea to just divide this up into triangles. All we're going to do again is find that g of negative 7 will be a positive number, and we'll multiply it by 2, since we're going to do the opposite of the area under that curve there. This is the triangle is 1/2 4 times 4, 1/2 of 16, which is equal to 8 in there. And this is going to be a 3 by 4 rectangle, so that is 12. And this technically it's -8 and -12, but we're going to make it opposite anyway. So it's going to become 20. This is going to end up being 2 times 20, which is equal to 40. As far as question 3 goes, I think that's going to be very easy to do because g of 9 and g of negative 9 are going to be the same number, but opposites of each other. So they will cancel out and make 0. You're going to have the integral from 0 to 9 and the integral from negative 9 to 0. Actually, oh, hold up. I disagree with myself. I contradict. I withdraw. Here's what's going to happen with g of 9 and g of negative 9. Oops. I don't want to get rid of my function. Oh, well. G of 9 is going to be, let's see, 5, 6, 7, 8, 9 over here. It's going to be that same triangle of 8, and this is a 4 by 1, 2, 3, 4, 5, 6, 7, 8, 9. So 1, 2, 3, 4, 5. A 4 by 5 rectangle will be 20. So this is going to equal 28 plus. Now we got to really think about this. On the area over here, the integral of g of negative 9 is the integral from 0 to negative 9 of f of t dt. That is equal to, we really got to think about this, this is equal to the negative integral from negative 9 to 0 of f of t dt. So the integral from negative 9 to 0 will be negative 28, and then we will make it negative again, so it's actually positive 28. So this ends up being 28 plus 28. Doubles itself, which will be 56. Nailed it. Now question B is going to do the same thing, but this time it's going to be an even function. It's the same set of questions, but now an even function will reflect over the y-axis. So it's going to change some of the problems. First of all, g of negative 3 is going to be the same answer as we had up here, only it's going to be negative. Since this is the integral from 0 to negative 3 of g of t, f of t dt, which is the opposite of the integral from negative 3 to 0 of f of t dt. So it'll be a negative 9 over 2. 2 times g of negative 7, you're going to, I think you might be seeing what's going on here. It's going to do the exact same thing as above, only negative. So this will be negative 40. And here's what's interesting. Question 3, B3, those are going to cancel out. Because what will happen is very similar to what happened here, is that the integral from 0 to negative 9 will be the same as the integral from 0 to positive 9, but then we're going to make it negative by switching the order of the bounds. So they'll actually cancel out and become 0. There we go. Hey, pretty cool. This ended up being almost 30 minutes, and I apologize for that. I know I've been giving you guys a lot of work to do lately, and I appreciate you keeping up with the pace of the class because it's going to keep rolling and rolling. You guys are doing awesome, and I appreciate you very much. You guys are great. I'll see you in the next video.